Okay, now we continue with the third part. So the scope of the previous two parts is to derive actually this final result, which says that the magnetization is linked to the magnetic field through this and temperature through this implicit relation. Okay, you remember Z is the number of nearest neighbors. So we recall here the small z is 2 times the dimensionality of the system. Okay. Good. We call this the mean field approximation of the Ising model. It's an approximation because we have not solved exactly the partition function. It's very difficult to do so for such an interacting system. Okay. We have done this through the Bogolyubov inequality, so we have found an approximation of the free energy, and that leads to this relation. Okay, so here we have the magnetization, and now also this is not analytically solvable as a relation, but we can do something, well, at least have a graphic solution to see what happens. The physics of this problem is relatively easy. Let's introduce a new variable y, and we write y is equal to m and y is equal to hyperbolic tangent of beta j z m. Okay, so and for the time being, let's set the magnetic field equal to 0. Okay, so a solution of this intersection of these two solutions, so the system of these two solutions is a solution of our original problem. Okay, but we can see how this looks like graphically. Graphically, we plot on the horizontal axis the magnetization, and on the vertical axis this new variable, auxiliary variable y. Okay, and therefore we look at the intersection of two curves. One is y is equal to m. Okay, and this is a line slope 45 degrees. Okay, and the other one is the y is equal hyperbolic tangent. Now you should recall how the hyperbolic tangent looks like, but when its argument goes to infinity, the hyperbolic tangent is equal to 1. So let's say that this is 1 and this is minus 1. Okay, so the hyperbolic tangent has the following shape. It starts asymptotically here. Okay, and goes to plus infinity and goes to plus 1 at infinity, at plus infinity. Okay, so and now we have to look at the intersection of these two curves. There is an intersection here in 0, 0. I recall you the hyperbolic tangent as the other function is an odd function, so if you take a negative value, then you get, so you take m negative, then you get a negative, so it's an odd function, sorry. So y of minus m is equal to minus y of m, okay? So both functions pass through 0, so there is always a solution of our system which is m equal to 0. Now the question, is this all? No, we can easily realize that this is not all, because I'm plotting here a special case. So particularly you see that if the temperature becomes small enough, so it means that beta goes to infinity, actually our hyperbolic tangent has a similar shape, but it becomes sharper and sharper close to the origin. And this would be the shape of the hyperbolic tangent at for high beta. So this is the low temperature case. So this one, let me indicate with the red color. This is low temperature, and this is the high temperature. So what does it mean? It means that here at low temperature we have more than one solution. We have namely three solutions of our problem. Okay. Therefore, our problem admits spontaneous magnetization. No, spontaneous magnetization is this intersection, which is there even in absence of a magnetic field. Okay, so what we are is this solution describing? Starting from high temperature, we have only one solution. Magnetization is equal to 0. This is the paramagnetic phase. However, when the temperature goes sufficiently small, then you have more solutions. And you have ferromagnetism, spontaneous magnetization. Now, you can ask yourself, so there will be a critical temperature in our problem, and this is the temperature at which, you know, that separates these two low and high temperature phases. And what is the critical temperature? Is the temperature that corresponds exactly to the situations where this curve is tangent, okay, to the diagonal. It comes out like this. Okay. So this is this third color. I hope you can see that this is a blue, this is TC. TC is characterized by having equal tangent to that point. So that if I lower the temperature just a little bit, then I go to the three intersections, and if I increase the temperature just a little bit, I go to one intersection. Okay. So to find this critical temperature, I have to ask when is this tangent and around this point around 0 equal to 1. Well, I can expand the hyperbolic tangent. Perhaps you remember that the hyperbolic, so let me do that for the original problem. So let me recall you that for small values of its argument, the hyperbolic tangent is equal to epsilon minus epsilon cube divided by 3. So for small epsilon, this is the Taylor expansion of the hyperbolic tangent. And the next term is of the order epsilon to the 5th. Why? Because hyperbolic tangent is an odd function of epsilon. Okay, therefore you don't have epsilon squared, you don't have epsilon to the 4th, and so on. Okay. Good. So this, therefore, this y at small epsilon becomes linear beta j z m, and this is the slope of this hyperbolic tangent. And so the critical temperature is when this beta j z is equal to 1. Or, if you remember, beta is 1 over kBt, or kBt is equal to jz. So this is the relation of the between the critical temperature and the parameters of our system. Okay. So in other words, our phase diagram of the Ising model, if I put here magnetic field and temperature, there is a critical temperature here. Here there is a paramagnetic phase at high temperature, and here there is spontaneous magnetization in this part. I call this a ferromagnetic phase, where you have three intersections, and these two are two phases, one with positive and one with negative magnetization, coexisting here at 0 field. Okay. So and now Tc depends on J and on Z. So let's try to understand this dependence. What is the dependence on J of this? What does it mean that Tc is linear in J? So if you increase the coupling term of your Ising Hamiltonian, so the strength of the coupling between spins, then you're pushing your ferromagnetic phase to higher and higher critical temperature. So it means that there is a stronger ferromagnetism in our system as soon as the J increases. Okay. Then Z, okay, and this is something we expect. Z is the number of nearest neighbor, the dimensionality of the lattice. And so if Z, the number of nearest neighbor, so if you go from 2 dimensions to 3 dimensions to 4 dimensions eventually, you see that every spin is more strongly coupled to neighboring spins. And also here the ferromagnetic phase increases. So we have a quite good understanding of these results, and is a result that follows our intuition. Okay, so this is the first result that of the critical temperature is equal to Jz. And if you compare to what is known for the Ising model in 2 and 3 dimension, in 2 dimension one can solve the model exactly. In 3 dimension one can find also an exact value for the critical temperature. This mean field approximation is reasonable. It gives a relatively good estimate of the critical temperature, and this approximation is better and better as soon as the dimension goes higher. We can consider 4-dimensional, 5-dimensional Ising model. Perhaps you're not familiar with higher dimensional system, but mathematically you can write down the Hamiltonian, we can solve the partition function, and we can ask, we can ask what is there magnetism, is there spontaneous magnetization, and so on. There is a critical temperature, or even for a 4-dimensional system. Okay, so this estimate of TC is quite good, and is getting better and better as soon as you go to higher temperature. Okay, so why is that so? Sorry, as soon as you go to higher and higher dimension. Why is it so? Because this is what we said, a mean field approximation. If you remember how we derived this, starting we treated this part exactly, and we treated the interaction in an approximate way. So we actually used a system of non-interacting spins as a starting point to define our free energy, and we used this part of the Hamiltonian. We treated that in this Bogoliubov approximation. Okay, so it is actually what we are doing in this system is treating this interacting part as every spin would be interacting with an average number of spins surrounding it. That's why it's called a mean field approximation. Okay. Now we can continue with the analysis of our problem. Now we have the result of the critical temperature. Let me write it here. So we find that KB TC is JZ. Let me erase this part. And we ask ourselves again, can we, are there critical exponents in our system? Okay, so can we define, as we did for the van der Waals model, critical exponents? So for instance, I want to look at T equal to Tc, so it means, let's fix the temperature to Tc. It means that here beta times J times Z is equal to 1. This is our critical temperature. And we are asking ourselves, what is the relation between magnetic field and magnetization? So we have hyperbolic tangent of M, and here we have beta C, so the critical temperature, times H. What is the relation between M and H? Again, we are around the critical point now, and we are looking at small behavior of the system in the vicinity of the critical point. So it means that both M and H are small variables, and therefore I can use again the approximation and expand the hyperbolic tangent in series in Taylor expansion. So we know that the first term is magnetization is linear plus time H then I have minus 1/3 m plus beta c times h to the third power. Okay. Now m and m goes away from here, and I have an h here. So I forget about the proportionality factors here, and I'm only looking at the dependence of h in magnetization. Okay, so if I do so, so I forget about the proportionality factors. Okay, h comes on this side, and on the other side I have m plus beta c h to the third. Okay, the lowest order term here is, well, I can write m to the third plus higher order term. Okay, so to lowest order, h scales as m to the third, and this defines an exponent delta, the equivalent exponent delta that we found in the van der Waals model. So we write this relation: h is m to the third. This is the exponent delta equal to 3. Okay. In the van der Waals model, we had delta p scales as delta v to the third. This is exactly the same story. Okay, so we are doing exactly the same type of analysis as the van der Waals model, and we find very similar results concerning, namely that all the thermodynamic quantities around the critical point behaves as power laws, and through this power law, the analysis of these power laws, we can define some critical exponents. Okay. For instance, what you can find is that, for instance, what we are asking ourselves, so what happens at m? So when I'm looking at values of the temperature which are below the critical point, okay, values of the temperature below the critical point, and now I do the analysis with the temperature. So you see, when I am at the critical point, I have this curve here, and I'm getting just a little bit below. So I have two intersections. These two intersections are initially very close to 0. Okay. And now my question is how this distance between these two intersections vanish as I approach the critical point. Again, I can expand this tangent hyperbolicus in power of using the Taylor expansion. But now I'm interested in the case where the magnetic field is 0. I want to see the spontaneous magnetization. So I only have that part containing m. Okay, if I set h equal to 0, again Taylor expansion tells me that this is beta j z m plus beta h, okay, plus sorry, there is no h here, minus 1/3 beta j z to the third m to the third. Okay, so 1m can be simplified here. From here I can get rid of 1m, this factor, and I get an m squared. Okay. Okay, so remember that beta critical times jz is equal to 1. So jz is 1 over beta critical. Okay. Therefore, here I can also write beta jz to the third from this one, m squared I can add a factor 1/3, but this is not so important. Yes, I bring this to this side, and here I have beta divided by beta c, which is this minus 1. Okay, beta c minus beta is also, beta c is critical temperature divided by T minus 1. Okay, therefore I get Tc minus T divided by T. Okay, and this is the relation. Now let me erase this line and write it here. Okay, so you see that when I'm close to the critical point, then I can expand beta around or the temperature around Tc. This will give beta is equal to beta c, therefore this is equal to 1 plus higher order term. This will give you T is equal to Tc plus higher order term. The lowest order term is that m squared is proportional to Tc minus T, or that m is proportional to the square root of Tc minus T, which means that the spontaneous magnetization goes to 0 as the square root of Tc minus T. Okay, this is another critical exponent. This square root is an exponent equal to 1/2. We have called this exponent beta in the van der Waals model. You remember, this is the exponent describing the difference of volume per particle, how this difference of these two coexisting phases goes to 0. Okay, so this tells me that if I'm looking at the magnetization, spontaneous magnetization, this is vanishing by approaching the critical point as a square root. Okay, this is a second critical exponent. Now there is a third critical exponent, which is the exponent gamma, and this is the exponent that describes the behavior of what is called the magnetic susceptibility. Okay, so how is this magnetization behaving? Well, the derivative of the magnetization with respect to the magnetic field calculated at h equal to 0 around the critical point. Okay, so again here I do the same analysis as before. Okay, so the magnetization, I expand the same relation as before. Okay, is equal to lowest order as beta divided by beta c times m plus beta times h. Okay, and I bring this to the other side, then I can find that m is equal to beta times beta c divided by beta c minus beta times h, and therefore the magnetic susceptibility is just given by this derivative. Okay, and so you see that, let me write it here, which is more clear. You see that chi is equal to beta times beta c and beta c is 1 over Tc, and so I can multiply the Kb on this side. 1 minus Tc minus 1 over T, okay, which is to lowest order is some constant divided by T minus Tc. Okay, so it's divergent as we approach the critical temperature, and is divergent with an exponent gamma equal to 1. You remember we defined an exponent to the power gamma. So we show now that the gamma is equal to 1. In other words, all the critical exponents that we derive from this analysis are identical to those that are obtained from the analysis of the van der Waals model.